Well, condition 1, make a nice table here. For the even solutions, condition 1 gives me e to the minus alpha L over 2 has to equal b cosine KL over 2. Condition 2 for the even functions is alpha a e to the minus alpha L over 2 equals kb sine KL over 2. For the odd functions, these will be slightly different. Like that. If I take the ratio of these two expressions, 1 and 2, this gives me tangent of KL over 2 is equal to alpha over k. On this side, the odds gives me cotangent KL over 2 equals minus alpha over k. Notice that k and alpha both depend on energy. Of the particle. And so these are transcendental equations, equations that can't be solved exactly for the energy, but it does give us a transcendental equation that's approximately solvable for the energy. And it's just because we have the argument of energy embedded inside of a tan function here and inside a polynomial over there. So that's something that can never be exactly solved. But we will define theta to be 2me over h bar over 2, which is KL over 2, and theta naught is 2m u naught over h bar over 2. In this case, these two expressions here reduce to, for the even case, tan theta is theta naught squared over theta squared minus 1. Take the square root. And for the odd, this is cotangent of theta is minus theta naught squared over theta squared minus 1. Take the square root. So it's theta naught squared over theta squared. This parameter theta naught is somewhat special. It's equal to L 2m u naught over h bar. Excuse me, 2h bar. It will determine the allowed values of theta, which is KL over 2. To find these solutions, we're going to plot the left-hand side and the right-hand side of these equations up here separately. And whenever this left-hand side graph equals the right-hand side graph, that's going to equal a solution. Solutions are going to occur for slightly less than odd multiples of pi over 2 for the even wave functions, and slightly less than even multiples of pi over 2 for the odd wave functions. Let's try to look at that. The solid line here represents the function tangent of theta. Plotted as a function of theta is KL over 2. And of course, tangent goes to minus infinity, it goes to plus infinity at pi over 2, and it comes from minus infinity so this pattern repeats. And of course, the tangent is 0 at pi, 0 at 2 pi, and 0 at 0. Again, this is just the even functions. That's plotting the left-hand side of the equation. Plotting the right-hand side of the equation, notice that this right-hand side goes to 0 when theta approaches theta naught. So it represents sort of an asymptote value. Below theta, when theta gets very small, this thing diverges, because this is 1 over theta squared. When theta approaches theta naught, this becomes 1 minus 1 is 0. So that's in fact what's happening. These functions are diving to 0 at some location, and it depends on the size of this potential. Here it's written V naught, but you should think of it as U naught, the maximum potential. So for small U naught, it dives to 0 rather quickly. For medium U naught, it dives to 0 rather later, and for large U naught, it dives to 0 way off to the right. So this represents the graph of the function alpha over k. Notice that there's always at least one bound state, because no matter how quickly this thing dives down, it will cross the tangent theta graph in one place at least. But for the larger U naught is, then it crosses the tangent theta graph in more places. So here's 3 such solutions, here's potentially more. The number of intersections where tangent theta equals this function alpha over k is the number of bound states there will be. And that makes intuitive sense. The deeper the potential well is, the more bound states I expect. In fact, I expect that these bound states are probably going to have something close to the energies of n squared h squared over 8ml squared. It's going to be a little less than that, actually, because we always said the curvature is less in the finite potential well. And if that was the case, I could kind of count up how many bound states there will be just by comparing U naught to the largest possible E sub n that would fit for the infinite potential law. And of course, as this function becomes more and more horizontal, in other words, u0 becomes infinitely large, this thing begins to approach the solutions of the infinite potential law, because when this thing is perfectly horizontal, it never actually comes down that far. It's way up here, and the tangent doesn't reach it until tangent gets really close to odd multiples of pi over 2. And when the tangent, when alpha of k equals an odd multiple of pi over 2, that exactly restores back my expected values for the infinite potential law. The odd solutions work very much the same way, except it's a cotangent function. To find the solutions for the odd functions, I just have to look at where the cotangent crosses this function minus alpha over k. And again, this function goes to 0 when theta approaches theta naught, and it goes to minus infinity when theta goes to 0. If theta naught gets to be very large, in other words, the potential well is very deep, this function becomes a near horizontal line. And the solutions occur closer and closer to the even multiples of pi over 2. There is pi, 2 pi, and so on. So again, I can never solve this exactly. I kind of have to make these approximate guesses as to where these intersections occur. And notice they're always going to be a little bit less than the exact solution for the infinite potential law when kl over 2 exactly equals a multiple of pi, 2 pi, and so on.